At our counting rules and also how they apply to probability here. We basically have three items here. We have what's called the fundamental counting rule, we have the combinations, and we have permutations. So we'll start out here with our fundamental counting rule. If there are m ways to do one thing and n ways to do a second thing, there are m times n ways to do both things. Quick example here, if a person has a choice of 4 shirts, 3 pairs of pants, and 2 pairs of shoes, there are 4 times 3 times 2, or 24 total ways to put shirts, pants, and shoes together. Basically, kind of the bottom line here is if we have different categories like we have here, we have shirts, pants, and shoes, those are categories, and we're going to select one out of each category, we multiply those total numbers together. So we multiply 4 times 3 times 2. That's our fundamental counting rule. We're choosing one out of each category to put together. M times n, or each of those categories multiplied together. A lot of our work will be with what's called our permutations and combinations. Permutations are an arrangement of objects in a particular order. To find the total number of permutations, you multiply the number of choices you have picking the object for each number by a succeeding object. Here's a formula for a permutation. I'm going to give you a shortcut version here. NPR, this is our total number of items to choose from. R is the number of items that we are selecting. And then we have N, our total number, factorial. Factorial is a math term with an exclamation point here that means to multiply each number by the number below it until we get to 1. So for example here, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. So hopefully we get the idea of a factorial. So here's our formula here itself, n factorial over n minus r factorial. There is a shortcut version of that. I'm going to show you that right now. It's on your graphing calculator, but let's just give it a quick example here. Let's say there are 20 people in our stats class, 20 total students. And for an experiment today, I'm going to say the first person done with their homework today gets, let's say $50. The second person done gets $25, and the third person done gets $10. Okay, so I'm going to give 3 places here. Okay, so obviously, at least I hope obviously, the order you finish in matters. It'd be better to finish first than third. I think most of us would agree we'd rather have $50 than $10. So this is a permutation. It's written this way: 20 total people to choose from, and we're going to award, in this case, 3 prizes. We're going to select 3 people, the first 3 people done. So as I mentioned, on a graphing calculator, there is a shortcut version of this formula. It's underneath the math function. At the top, we have choices of numbers, complex, and probability. We're going to choose probability. And notice we go down to number 2, that's an NPR. So I'm going to go down, I should have gone down that to begin with, but I just want to show where that's at. So I'm going to clear out of here. And now I need to put my number in first, 20. Now go to my probability function, down to NPR. It's going to put that in there, and then I put my 3 in there at the end, and that's going to tell me there are 6,840 ways for you 20 or 20 students to finish first, second, or third. Okay, so permutation, once again, the order or the arrangement of the objects does matter. And we just covered the idea of a factorial there as well. Now, combinations are simply the possible groups of objects. So let's go to the same example. Instead of first getting 50, second getting 25, and third getting 10, first place is going to get 25, second place is going to get 25, and third place is going to get 25. So notice it doesn't matter if you finished first, second, or third, you're still going to get the same prize. So the order we finish in doesn't matter. We all get the same prize. That makes it a combination. The formula itself is right over here. N factorial over n minus r factorial times r factorial. And again, there is a function on the calculator that makes this simpler. 20 people to choose from. It's a combination, and we're going to select 3. So I'm going to show you that as well. Type in our 20. Go here to math, over to probability, and notice down number 3 is an NCR function. So we're going to put 20C3, and there are 1,140 combinations 1140 here, and there was 6840, I think was the number up here. So a lot more permutations because the order matters as opposed to combination where the order does not matter. So there's the basic distinction between the two items there, permutations and combinations. Biggest thing, order matters with permutations, order does not matter. We're just arranging objects with combinations. We'll run through a handful of examples that will hopefully illustrate these ideas. Student has a choice of 3 sections of English, 4 of math, 2 of science, and 5 of history. How many different schedules are possible if a student takes 1 section of each of these courses? Because we're going to take 1 out of each of these categories, that makes it a fundamental counting rule. So we simply take 3 sections of English times our 4 types of math, our 2 of science, and our 5 of history. And if we multiply those, we have 120 different schedules that we can put together based on those courses being available to us. Okay, so there's our fundamental counting rule. Moving on here, manager wants to visit 6 different cities where the company has branch offices. Ooh, maybe I didn't go all the way to the top. Let's go all the way to the top. Baseball. How many different baseball batting lineups are possible? For 9 players, the coach wants to put one of the 2 best hitters in the 3rd position and wants the pitcher to bat last. In these situations where we have special criteria to meet, 2 best hitters in the 3rd position, pitcher batting last, it might be easier, or it is easier, to set up blanks 3, 4, 5, 6, 7, 8, 9. In this case, for all 9 positions in our batting order and filling in our 2 criteria. So in this case, we want one of our 2 best hitters, one of the 2, to bat 3rd. So one of those 2 batters can bat in the 3rd position. We also want the pitcher to bat last, so only the pitcher can bat here, and we only have 1 choice. So with that being said, even though I have the number 2 here, there's only one of those 2 batters going to be here. The other one is available to bat anywhere. So if I have a batter here and a batter here, that means 7 batters are left to bat leadoff, 6 to bat second, 5 to bat cleanup, 4, 3, 2, and 1. And we're going to multiply those together to find our number of ways to put that lineup together. And there are 10,080 different baseball batting lineups with 9 players matching those 2 criteria. Manager wants to visit 6 different cities where the company has branch offices. How many different ways are to visit the 6 cities? I'm going to start the same way. 3, 4, 5, 6. If we're going to visit the 6 cities, I can visit any one of those 6 cities to begin with. Once I've visited, say, New York, now there are 5 cities left to visit after that. I've gone to Chicago, so now there are 4 cities. Gone to Boston, there are 3 cities. Gone to New York, to Los Angeles, 2 cities, and I can end up in San Diego. And here we're going to multiply those together. Notice that looks like what I had written on that first page. That's the same thing as 6 factorial. Or, because we're visiting cities, the order that we visit those cities in, I talked about New York and Chicago and Boston. It's a lot different going from New York to LA, back to Boston to Chicago, as opposed to going to New York, Boston, Chicago, and that way. So that'd be the same thing as 6p6. Either way, we're going to get 720 ways to visit those 6 cities. Okay, how many different ways can 1st, 2nd, and 3rd place be awarded to 7 contestants? We're talking about 1st place, 2nd place, 3rd place. So finishing order matters. I'm going to start with blanks, 3. There are 7 people that can finish 1st. Once we have a 1st place finisher, 6 people can finish 2nd, and 5 left to finish 3rd. That's the same thing as 7p3. We're awarding 3 prizes, or 3 places, 1st, 2nd, and 3rd. Each one has a different label, so it's a permutation. And there are 210 ways that we can finish 1st, 2nd, or 3rd with 7 people. 7 times 6 times 5, or 7p3. 3 children in a class of 17 are going to be picked to be awarded prizes for a writing contest. How many possible ways are to pick winners if each prize is different? Here's the key statement here. Each prize is different. I'm going to go one more time with the blanks. 17 people can win the 1st prize, 16 people the 2nd prize, and 15 people the 3rd prize. Now, I pointed out that each prize is different. That makes it a permutation. It's like my 50, 25, and 10 idea. If each prize is different, the order you finish in makes a difference. And 17 P5 or 17 times 16 times 15 is 4,080 ways to finish or get those three winners. Each prize is different. So notice how that one's different than our next one. How many ways can 5 scholarships of $1,000 be given to 5 students from a group of 15 applicants? So here we're selecting 5 scholarship winners, 5 students out of a group of 15, and each one's going to get $1,000. So it doesn't matter whether the first person selected or the 5th person selected, you're still getting $1,000. So that makes it a combination. We have 15 people to choose from, and we're choosing 5 to be awarded prizes. So it's a combination of 15C5, and 15C5 is 3,003. That's from the calculator. Let's keep going here. How many ways can 3 people be picked from 10 to be on a committee? 3 people on a committee, doesn't matter what order we put them on a committee, they're just on the committee. So it's a combination of 10C3, and that would be 120 ways. Now if I change the wording and said we're going to put those 3 people on, and one's a president, one's a vice president, one's a treasurer, now the order they are selected and makes a difference because they have different labels, then it becomes a permutation. But we're just putting 3 random people on a committee in no particular order, so we have 120 ways where it's a combination. A bowl contains 6 black and 5 white marbles. How many ways can 2 black and 3 white marbles be drawn out? Here we have 2 different categories. We have 6 black, and we want to draw out 2. Does it matter what order we draw the black marbles out in? No, so it's 6C2. Times, we also have white marbles. We have 5, and we're going to choose 3. So the order we draw the white marbles out doesn't make a difference, so it's 5C3. And notice I multiplied those 2 different combinations together. How many ways? Which means we have 150 ways when we plug that into our graphing calculator using that combination function. One more time here on this page, how many ways can 3 5th graders be chosen from 8 5th graders and 2 4th graders be chosen from 5 4th graders? So notice we have 8 total 5th graders, and we're going to choose 3, 8C3. Should have made this point earlier, but anytime we want a combination or a permutation, the total goes first. How many we're selecting goes second. So essentially, this second number will never be larger than the first number. The first number is always either equal to or typically larger than the second number. Going back to our problem, we have 5 total 4th graders, and of those we're going to select 2. So 8C3 times 5C2, and that gets us 560 ways to select those 4th and 5th graders. Noticing a little bit of a change here. A box contains 24 transistors, 4 of which are defective. So 4 are defective, which means 20 work. If 4 are sold at random, find the following probabilities. Okay, our last several problems just said how many. This says to find probability. We've established since day 1 with our probability that probability is a fraction. So I'm going to start here with my denominator. My denominator is my total number of possible outcomes. Okay, I have 24 total transistors to choose from. I'm going to sell 4 of those. Does it matter what order I sell those 4 in? No, I'm just selling 4 transistors, so it's a combination of 24C4. That will tell me the different number of ways that I can sell 4 transistors. Now, going to the top of my 24, we have 2 categories of those. We have 4 that are defective, and we have 20 that are not defective. So the first thing I would note, my 24 is broken out of these 2 categories. 4 and 24 add to be 24. Now I'm going to meet these 2 criteria. This criteria, exactly 2 are defective. So of the 4 that are defective, I want to sell exactly 2. Which means of the 20 that work properly, if I'm selling a total of 4 and 2 of those are defective, that means 2 of those work properly. So notice that the 2 plus the 2 equals the 4 here. 4C2 times 20C2 over 24C4. So we've tied our numerator and denominator together. The 20 and the 4 had to be 24. The 2 and the 2 had to be 4. We can go ahead and make our calculations. And as a decimal, that's 0.107. Or as a fraction, that's 190 over 1771. We can take either answer, one or the other. Let's continue on then with our next one. None are defective. starting with our denominator, still 24C4, total number of ways we can sell 4 transistors. I'll set up my 2 categories here, 4 that are defective, 20 that are not. This time I want to sell none being defective, so 4C0, which means of the 20 that are not defective, we want to sell 4. Again, pointing out 4 plus 20 equals 24, and 0, try that again, 0 plus 4 equals 4. So our numerator and denominator match up. Quick little side note here, 4C0, anything that has a 0 second for our C has a value of 1, so it's a little bit of a shortcut with our calculator. 20C4 over 24C4 gets me a decimal of 0.456, or a fraction of 1615 over 3542. Let's keep rolling on here. All are defective. Still finding probability, so 24C4. Still have our 2 categories, 4 that are defective, 20 that are not. This time, all 4 that we sell want to be defective, so 4C4, which means of the ones that are not defective, we're not going to sell any this time. And another side note here, 4C4 has a value of 1, 20C0 has a value of 1, so I can shortcut my numerator to be just 1 over 24C4, which is 10,626, or as a decimal, that's 0.0000941. And one more time, at least one is defective. Remember back in our last section we talked about the at least one part. Easier version is 1 minus the probability, in this case none being defective. So the good news is back here in step B we found none being defective, so it's 1 minus the 0.456, which is 0.544, or 1 minus 1615 over 3542, which is 1927 over 3542. So again, fraction or a decimal, we can take either one. You don't have to have both, just one or the other. But there's our first look at probability with our combinations. Delivery route for a bread truck consists of 5 different stops. If the 5 stops are picked in random order, find the probability of picking the most effective one. Noting again, we're finding probability, so I'm going to start with my fraction bar. Noting that first of all, I have 5 different stops to make here in my denominator. 5, 3, 5. As I make those stops, it doesn't matter what order or first stop I can make, I guess I should say. I have 5 to choose from. 4, 3, 2, 1. Make any one of those 5 stops first, followed by second, third, fourth, and fifth. So my denominator is the same thing as 5 factorial, or 120. There's 120 different ways to make this delivery route. A little bit tricky here. We have to read into this a little bit. It says the most effective one. There's only one most effective route, so it's 1 out of 120. Most effective one. Another time here, network chooses 3 shows put on Monday night. They choose the order of shows at random. What is the probability that you have the best order for viewer satisfaction? Probability, fraction bar. So I have 3 times 2 times 1 here, or a denominator of 6. Best order for viewer satisfaction, there's only one best order, so our probability is 1/6. And I believe we have 2 problems left to finish here. Farmer has 3 fields to plant. He has a choice of 8 types of cotton, 6 types of corn, and 3 types of soybeans. If he picks 3 crops at random, find the probability that he will plant 2 fields of cotton and 1 of corn. So we're finding probability again, fraction bar. As we read through here, 8, 6, and 4, he has 17 different crops to choose from. Of those 17, he's only going to plant 3. So my denominator is 17C3. Doesn't matter what order he plants those crops in, he's just going to plant 3 different crops. So a combination. Of our crops, our 17 crops, we have 8 that are cotton, we have 6 that are corn, and we have 3 that are soybeans. So notice the 8, the 6, and the 3 add to be 17. These are our 3 different categories. Of the 8 types of cotton, he wants to plant exactly 2, so 8C2, times, of the 6 types of corn, he wants to plant exactly 1 of corn, times, of the 3 types of soybeans, he's not going to plant any, so 3C0. Again, noting 3C0 is going to have a value of 1 if you want to take any kind of shortcut at all. Now, all we have to do, if we have that set up, is type that into our calculator. As a decimal, that's about 2.247. As a fraction, that is 21/85. One more time here. A teacher has a choice of 16 different difficult problems or 5 very difficult problems. It is a short quiz with 4 questions, and the problems are chosen at random. What is the probability of having 2 difficult and 2 very difficult problems on the quiz? Probability, starting with my fraction bar. I have a total of 21 questions to choose from. Of those 21, I'm going to put 4 on the quiz, so 21C4. There's my denominator. Doesn't matter what order I put those questions on the quiz, I'm just putting 4 random questions on the quiz. Of those 4, or of those 21, 16 are difficult and 5 are very difficult. There's our 2 categories, difficult and very difficult. 16 and 5 add to be 21. And we want to put 2 of each on the quiz. So 16C2 times 5C2 over 21C4. Noting how our numerator and denominator match up, and that winds up being a decimal of about 0.2005, or as a fraction, that's 80/399. And there's a look at our counting rules along with probability and the